Welcome to The Explainer. Today, we're taking the foundational concepts from Dr. Shemaya Zaidan's basic echocardiography course and breaking down the core principles of echo Doppler. Whether you're a cardiology resident, a fellow, or a junior consultant looking to sharpen those bedside diagnostic skills, well, you're in exactly the right place. We're going to really break down the mechanics of sound waves so you can elevate your clinical interpretation and just make much more confident bedside decisions. Let's get started.
Okay, let's dive right into this. Our roadmap today has 4 key stops. First up, the everyday Doppler effect. Second, bat sonar and echolocation. Third, we're bridging biology to cardiology. And finally, we'll wrap up with essential clinical applications. So we're going to build this from intuitive, real-world physics all the way up to those critical bedside applications.
All right, Section 1, the everyday Doppler effect, experiencing physics. Before we start staring at complex spectral waveforms and color maps on a screen, I want to remind you that you actually already intuitively understand the core physics of Doppler. You probably just don't realize it yet.
Think about it. Every single time you stand on a sidewalk and hear an ambulance passing by, you are directly experiencing Doppler physics, right? As it speeds toward you, those sound waves compress, and that creates a higher frequency or a higher pitch. Then, as it speeds away, the waves stretch out and the pitch drops. That relative frequency shift, that's literally the Doppler effect in action. It's an absolutely crucial, foundational analogy that we need to keep in our heads as we start evaluating the cardiovascular system.
Let's move to Section 2 and see how this builds. Section 2 is bat sonar and echolocation, flying echo machines. We're shifting our focus from busy city streets to the animal kingdom's absolute mastery of sound waves.
In her lecture, Dr. Zaidan brilliantly refers to bats as flying echo machines. And honestly, think about this incredible adaptation for a second. Bats rely on this highly sophisticated biological radar system to essentially see with sound in complete darkness. No way, right? They don't use light. They use acoustic echoes to navigate these incredibly complex cave systems and hunt prey with absolute pinpoint accuracy.
So how exactly do they do it? Well, it operates on a simple, elegant 3-step sequence. Step 1, sending out high-frequency ultrasound waves, which, by the way, is exactly like our piezoelectric crystals. Step 2, actively listening to the returning echoes bouncing off objects like, say, a moth fluttering in the night sky. And Step 3, instant interpretation. I want you to pause and think about this for a second. This simple 3-part natural process, sending, listening, and interpreting, is exactly what our complex ultrasound machines are programmed to do at the bedside.
So the crucial point here is understanding the incredibly rich data this natural motion detection system gathers. By analyzing those returning echoes, bats determine 4 vital parameters. Distance, is the target near or far? Motion, is it moving or stationary? The specific direction of that movement, and finally, the size of the objects. Now, for those of you learning echocardiography, here is your first major clinical pearl to take away. These 4 parameters, distance, motion, direction, and size, are the exact same data points we use to track red blood cells right through the chambers and valves of the heart. Which brings us to Section 3, bridging biology to cardiology, from caves to the clinic. It's time for that conceptual aha moment, where we directly connect the bat's natural radar mechanics to human cardiac physiology.
I absolutely love this quote straight from the source material. What bats do naturally in caves, we do in cardiology. I mean, it's a really profound realization. Clinical echocardiography isn't just some intimidating, arbitrary technology. It's actually just a human-engineered extension of a brilliant, naturally occurring biological adaptation. Just as the bat's brain processes sound waves to visualize that moth, the modern echo machine acts as our own sophisticated biological radar. That transducer probe you hold in your hand, it sends ultrasound waves into the chest, listens for the echoes bouncing off moving red blood cells, which creates that vital frequency shift we talked about, and then its internal processor translates those echoes into the dynamic, real-time images you see right there on the screen.
Now, what's really interesting about this slide is that when we look at actual spectral waveforms and color flow mapping, we are literally seeing the bat's echolocation translated into clinical data. Just like the bat figuring out the direction and speed of its prey, these waveforms directly represent the motion, direction, and velocity of moving blood within the heart. Blood moving towards your transducer creates a positive frequency shift, so it's displayed above the baseline. Blood moving away, that creates a negative shift, shown below it. It's that ambulance siren effect, just happening at a microscopic level inside the ventricles and atria.
All right, let's transition to our final and honestly most critical section. Section 4, Essential Clinical Applications. This is where we take our theoretical physics framework and turn it into practical, life-saving diagnostic tools. So why does Doppler matter so much?
It matters because it's the absolute cornerstone of modern cardiac assessment. Let's rapidly map this physics to the bedside. We use Doppler to quantify valve stenosis, measuring exactly how fast blood is forced through a narrowed opening using the Bernoulli equation. We use color Doppler to assess valve regurgitation, easily spotting blood flowing backward where it definitely shouldn't be. Down in the ICU, it is a total game changer for hemodynamic assessment in shock, allowing us to estimate cardiac output and pulmonary pressures instantly. And here's a massive clinical pearl for you. 2D echo gives you a picture of structural anatomy, but Doppler gives you real-time, dynamic physiology. So I'm going to leave you with this final provocative question to reflect on. How will mastering these basic principles of sound transform your diagnostic accuracy at the bedside? Because when you truly internalize that an echo machine is really just a highly sophisticated application of everyday physics, from passing ambulances to navigating bats, you stop just memorizing textbook values and you start deeply understanding the living physiology right in front of you. Thanks for joining us on this explainer. Keep learning, keep questioning, and always look closely at the data. See you next time.